When we studied functions in the past, we used this notation. If we had an equation like y equals this expression involving x, we could say that f of x is equal to this expression. Now, this is a function in one variable. And now we're going to study situations where we have functions in two variables. And all it means is that the expression over here involves more than one variable. So f of x and y, you see, means a function involving these two letters. So we have some expression and they involve these two letters. And the idea of evaluating for particular values of x and y can be requested using the function notation. F of 2, 3 means in this f function, replace x with 2 and y with 3 and evaluate. So over here we would have 2 times 2 squared minus 3 squared. And evaluating, let's see, 2 squared is 4 times 2 is 8, minus 9, oh, that's negative 1. Here's another one, f of x, y, z. Well, let's see, here's a function involving three variables. And all we're looking for, once we see this notation, we just know that we're kind of looking for an expression over here involving three letters, and those letters are x, y, and z. And that's really all there is to it. If we want to evaluate, find the value of the function when x is 0, y is negative 1, z is 4, we just plug these values in. So we would have e to the, well, let's see, x is replaced with 0, y is replaced with negative 1, z is replaced with 4, and we evaluate. Now e to the 0 is 1, so this is negative 1 plus 4, oh, that's 3. Suppose we want to find the domain and range of this function involving the two variables x and y. And here's the function. Now we go back, when we have a request like this, we just go back to our basic understanding and of the meaning of domain and range. Domain, the acceptable replacements for x. That's the way we thought about it before. The acceptable replacements. The replacement values that make sense in the context of the expression. Well, let's see, the values for x and y which make sense in the context of this expression would be those values of x and y that would cause this radical business to make sense. And radicals make sense when the radicands, I shouldn't say all radicals, I should say square roots, make sense when the radicand is positive or 0. So we would like to indicate for the domain that this radicand must be positive or 0. So we just say that the expression under the radical is greater than or equal to 0. Now we can actually massage this a little bit, change its form just a little bit into x squared plus y squared is less than or equal to 64. Now you notice to do that I kick the 64 to the other side, and to change these signs I multiply through or divide through by negative 1, and that changes the sense of the inequality. Now the implication here, this is the domain, that's a nice description of the domain, but the implication here is that x and y, better make this an x and y can't be numbers that are any larger than 8. So x has to be less than or equal to 8, y has to be less than or equal to 8 as well in order for this to be true. Now this information helps us to find the range. Now the range, even when we studied it before, is a rather elusive kind of thing. It's the notion that once we've established the domain, for the range we're asking ourselves, gee, what values can the expression take on? As the expression takes on all values within its domain, what values emerge out of that expression? And in order to make the evaluation of f of x is equal to some function of x, we said, okay, let's let the expression be equal to y. Let's say y equals this expression in x, and now we can evaluate the values of y. Well, here we have a function in x and y. And to evaluate this, we might say, all right, let's let z equal this. You see, so we could say that z is equal to this expression. And now, if x and y take on the value, their lowest possible value, let's say 0, then z would be 64 minus 0 minus 0. Oh, z would be 8. So that's the smallest value that x and y can be. All right, what if we go to the top end? If x or y is equal to 8, then You see that x or y is, let's slide up here. If x or y is equal to 8, then squaring we get 64, and we would have a situation where the smallest value of this expression is going to be 0. So if x or y is 8, then z is equal to 0. So z will fall within a range from 0 to 8. So here then is our range. Associated with our study here is the notion of a contour map. And contour maps are part of topology and relief maps and so forth. They try to give some information about a depth perception. And that's what this study in a three-dimensional coordinate system is all about. We would like to be able to write equations and functions and give illustrations that are three-dimensional in nature. Now, a contour map involves this idea. Suppose, just for a moment, now let's just imagine that I can, as I climb a gently sloping hill, that I have an altimeter on my arm, and I can measure the altitude at various points on my path. And as I travel up the hill, let's say I'm measuring in increments of 100 feet. And every time I go up another 100 feet, I make a mark. And then, after I make the mark, I walk all the way around that mountain at that level. It's impossible, but imagine it. Stay with me here. All right, so I march all the way around, and I leave a trail of white paint all the way around the mountain at that altitude of 100 feet. And then I go up another 100 feet. I travel a little farther, go up to the 200-foot level, above sea level, you see. And then I do the same thing. I walk all the way around the mountain at the 200-foot level. And then I do the same thing at 300 feet, 400 feet, and so on. Now I have all of these circles, sort of. They're not exactly circular, are they? They're just paths of white paint. I can't really see them too well if I'm looking from the bottom of the mountain. But what if I get up in the space shuttle and I look down with a telescope and I'm looking straight down on top of that mountain, and I see all of these white paths. You see, those white paths would be at different altitudes. And it would take on a configuration that might look something like this. And that's what a contour map is all about. Now, what this really is, that each one of these represents a different altitude, if you will. And each one of these is called a level curve. And all these are just traces that are projected upon the XY plane. I mean, think of it like this. That's kind of a mouthful about this projection idea, but now the XY plane is sort of the flat surface here, let's say. That's what the idea is. And Z represents sort of height. And so each one of these would be a different altitude. So it is as though we take a trace at a particular Z level. Boom. We take a trace. That's that white path around the mountain. And then we just take that trace and project it onto the XY plane. Print it. You see, go up to another level, find the trace, print it. You see, all we're doing is just projecting those traces onto, boom, the XY plane, and we have a map that looks like this. Now, when you first look at a map like this without any indicator of what these lines stand for, you don't know whether you are talking about a valley right here. You see, this could be the low point in the situation. We have a low point in a valley in these two places, and these lines indicate rising from the valley. Or it could be that these are the peaks of a couple of mountain peaks here, and that these represent altitudes which are going down the mountain on either side. So you really don't know until you look at the values associated with these level curves. All right, so that's the idea. An example of a function in two variables is the Cobb-Douglas production function. and it is some units produced as a function of labor and capital. X is the units of labor, Y the units of capital. The units produced is a function of labor and capital. All right, so that's the idea. And f of xy then is c times x to the a, y to the 1 minus a. This is the form that this family of functions appears in. C is a constant now, and a is a number between 0 and 1. Okay, a particular function in this Cobb-Douglas production function family would be this as an example. F of xy is equal to this expression. Now, x is measured in person hours and y is measured in thousands of dollars, and we'd like to know the production level when x is 1,000 and y is 500. And all we do is plug in, just as we would with any other function, f of 1,000 comma 500 means replace x with 1,000 and replace y with 500 and evaluate the expression. So we just pop 1,000 in place of the x from up there and 500 in place of y, punch the calculator, and we find the number of units under these circumstances to be 75,786.